Os presento a Rodrigo Vidal, que es investigador de la Universidad de Santiago de Chile y es una de las personas que trabaja en la secuenciación del genoma de salmón, junto con un equipo canadiense y un equipo noruego. El salmón es una de las especies más importantes en acuicultura, entonces de ahí el interés en la secuenciación del salmón. Él está especialmente interesado en la relación entre el genoma y diversas patologías. Entonces ya empezaré con la charla.
Gracias, Paloma. Okay, thank you. Good morning, everyone. My talk is in English, but it's very strange because the number of the people that speak Spanish is huge, that the people that speak in English. But anyway, I think that this is important because currently there are other people in another part of this world maybe looking this talk. Okay, first, thank you very much to Paloma, thank you very much to the University of Vigo, to the opportunity to present just some part of my investigation of my group. Anyway, here is a lot of people involved in this work, the people from Norway, the people from Canada, the people from Australia, of course, another group of Chile. In the future, I hope it's people from Spain, Principal Paloma. Okay, my research and my interest of my group is in link of transcriptomic and immunoresponse. We call it this mixed immunogenomics. This is link between genomics, principal structural genomics and functional genomics, and the immunoresponse. So the focus of my talk today is in two principal diseases, very important to Chile, very important to another country, principal Norway, principal Canada, Island, Faroe. So when we heard the name of Chile, maybe the first is to think it's a long country, and it's really, we have a long country. But the principal focus of our area of aquaculture is in the southern of Chile, the Puerto Montt to the southern. And the northern of Chile, principal, you can see there, Santiago is in the middle, and the first green is the northern of Chile, in city called Coquimbo and Caldera, is just about 3% of nothing more aquaculture. The principal species in the northern of Chile with the focus of the production is flatfish like turbot, a little of mussel, and nothing more. So about the 95% of the production of the aquaculture in Chile it's the focus of the southern of Chile. It's very funny because it's not aquaculture, it's salmoniculture. But the principal species that we cultivate in the southern of Chile is salmon. The principal species that my country focus is Atlantic salmon, coho salmon, chinook, rainbow trout, and in the northern of Chile as turbot. But of course, the most important, because the price on the market, this is a business issue, is Atlantic salmon. In second term is coho and rainbow trout. So we have a focus in salmonid. For my country, the salmoniculture is a very principal interest because it's a field of the principal economic importance and the social importance, of course. The salmonid is a very complex group of species because they have a big problem. It's the duplication. More or less 50 or 60 million ago, we have the first duplication in this group of species. And you can see in these three different species, and a lot of species have a genome project working now. For instance, cod, medaka, tilapia, and there are other model species like fugu or turtledon with their own genome project. So in this moment, in this group of the salmon on truth, we don't have any project. But currently, we are working in the Genome Mouse project. It's a consortium between Canada, Norway, and Chile to sequence the all genome of salmon, Atlantic salmon. And there are another group with France and USA and maybe Chile. We are thinking to start another genome project to sequence all the complete genome of salmon trout. So the first problem we to face with this species is the genome size is very huge. It's big. It's more or less the same genome of any human, about 300 million per base, and more or less 13 or 25,000 gene. So it's a huge genome, and with the duplication, it's more complicated. So when we start to work in the genome of salmon, we know that's a problem. And of course, we know it's a very, very, very complex challenge to try to study this genome. In any process of the industrial culture, like salmoniculture, the principal problem to see in this culture is the disease and the diet, nutrition. There are two principal problems, disease and nutrition. In the case of disease, of course, we have an overlap of issue, the pathogen, virus, bacteria, of course, the host, but any species, the immune response of any species is very different. Just one example, for instance, to ISA is a very important virus, but the salmon coho is resistant to ISA, but Atlantic salmon, no. Both species are salmonid, but are in different genus. But the first question is, why one species is resistant and why another species is susceptible? It's very interesting. Another issue in this area is the environmental. But in the cultivar, all the people try to control in the best way possible the environmental. So the principal idea here is the diet, because there are a big problem to feed all the fish. Why? 10 years ago, the principal diet, the principal origin of the protein in the diet is animal protein. But currently, the protein in the diet is very expensive. But the principal origin of the protein in this diet is the fish. But there are not more fish. So it's very, very expensive. So it's necessary to make a change to the protein diet from animal to the vegetal diet. So the question is, what is the impact in one animal that natural origin of the protein is animal if you feed with this species with vegetal protein? What is the impact in the immunological response? What is the impact in the growing? There are many, 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 many questions. So the principal impact, of course, of any crisis of virus or bacteria is a decrease of production. And that is the principal real interest for my country. How is possible to lower the number of the diet individual when we have an outbreak of disease? We have many alternatives. Vaccine, for instance, immunostimulant, for instance. But the idea is, this alternative work well or no? So maybe some in this room, maybe any people from maybe this room saw this film. It's a typical film from Hollywood. The name is A Perfect Storm. It's a typical history. It's a fisherman with a principal interest in cod, and this fisherman in the Atlantic North go to the sea. In this moment, this fisherman find on two storms, and this storm overlap, and he is in his boat is in the middle. So the same idea I have 4 years ago, when we have an economic crisis, a world economic crisis, and the first outbreak of the ISA, plus another virus, IPN, plus bacteria, and plus one parasite, Caligus. So if you merge economic crisis with all this disease, we have the perfect storm. It's a very, very complicated situation. So we have this problem. We have our first perfect storm 4 years ago. So in this moment, the government of Chile say, okay, guys, we need solution. We need solution for this problem. In this moment, we talk with the government and say, okay, we work in disease, we work in nutrition, and we work in stress. We have a lot of data in each of the three areas, but we will focus in this talk in disease. So, what is a normal application of the know-how in salmoniculture? We have maybe 3 steps. We have prevention. Of course, we give to all the individual immunostimulant, antivirals. That is very complicated. With antiviral, maybe create resistance. We try to allow the stress, because all the people know that we have stress. The response of to virus or bacteria is very low. And after, we have diagnosis. Screening, looking new pathology, stress evaluation, and diet evaluation. And then we have the third and the last step, therapy. The principal therapy now is vaccine. Well, but everyone in this room know that the vaccine don't work very well. The cover of the vaccine in all group is not perfect. So any people in animal production think that I put one vaccine in any individuals or any group of individuals, I hope that they will have a cover of 100% of protection. But the reality is not that. We have 15, 14% of protection. So we have 16% of the animal with vaccine that died. So what happened? What is the problem? The problem is the vaccine. Of course, we can think the vaccine don't work. Yes, maybe it's one alternative. Or we can think also that this individual, that this strain, that this family don't respond for this particular vaccine. Maybe the vaccine is very good, but the problem is not the vaccine. The problem is in the response of this strain. So what is necessary? We need a lot of vaccine for every particular strain, for every particular species, for every particular group? Maybe. In human, now, this is called personalized medicine. Now, we know that every group, every family respond in one particular way. So, this therapy needs to make an evolution to the next step, that the next step is we need a vaccine to every particular group. Now in my country, in all the world, when I think in all the world, it's not all the world, it's just 3 or 4 parts of this world. I think in Chile, Norway, Canada, Islas Feroe, Irlanda, nothing more. The principal country with salmoniculture activity. But this country, now, if we can look how many vaccines are in the market to ISA 1011, to IPN 6 vaccine. So we have a lot of vaccine to choose. Okay. The genetics, is very old. The first application of the empirical genetics is very, very old. But we can see that the genomics is very new, just 10 years ago. 10 years ago, more or less. When started the post-genomic era? Maybe with the first release of the first draft of the human genome with Craig Venter, 10 years ago, 11 years ago. In this moment, start post-genomic area. Why? Maybe because the people think that the more complex genome published was the human. Of course, before of the genome come another genome very important, and after of genome there are many genome of bacteria, but bacteria is a very simple organism. So maybe when we can mark or put a flag in the time when start the post-genomics area is with the release of the first draft of the human genome, because again it's a more complex organism. So we have just the history in my area, 10 years. It's a few years. So we have the typical cascade when you can start with the structural genome, and then we pass to the functional genomics or transcriptomics, and then we can pass to the proteomics, and then functionomics, morphonomics, and believe me, you can go then to glycogenomics, spliceomics, metabolomics, lipidomics, epigenomics, and blah, 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 blah. And it's not a comics, it's really. And many people that just concentrate in just one particular area, with glycogenomics, for instance. So the most important here is that to go to this step, for instance, proteomic, you need, after, a good transcriptomic. Of course, if you can start here in this area, transcriptomic, you need a good genome. It's very complicated to pass from structural genomics or genomics and go to the functional genomics, for instance, or proteomics. It's very complicated. So the principal idea is it's necessary for everyone go step by step. I want mean to the genome, to the functional genomics, to the proteomics, and then it's very complicated to try to start from the structural genomics and go immediately to the proteomics. Why? It's very easy. Because we need the gene. Without gene, just we can see with proteomics a spot everywhere. Maybe many people here have the opportunity to see the gene of the proteomic 2D, typical 2D and 2D dimension. It's just a spot. But we can sequence this spot with mass spectromic. But if we don't know the gene, we don't know what is this spot. So it's complicated. So 2 years ago, we start with an international consortium to sequencing the Atlantic genome, like a reference of the genome of all the salmonids. And believe me, it's a very, very, very complicated organisms. Maybe the most important and most complicated organism sequenced in the history. It's very complicated. There are many people working in this project. Of course, there are 3 countries, but there are many people at JCBI, Craig Venturi Institute, people for Institute of Beijing in China, people working on the France. There are many people trying to help in this genome, but it's very complicated. And the principal complication of the genome are the duplication and the repetition. There are a lot of repetition. What is the problem with the duplication? The typical fate of the one duplication is to make a copy, and this copy degenerate, and this copy continues being functional. This is the typical way of one duplication. The typical history what any people teach in any classroom. Okay, of course, they are just paralogous copy, and this copy degenerate. But currently, we know that at least 2 alternatives more. Second alternative, of course, we have one duplication, any duplication, but this copy is not degenerate. This copy acquires a new function. And the last alternative is this copy now is a subfunctionalization. So we have 2 alternatives more than the classical alternative. For this, it's very complicated. So I think that it's necessary to have glycomics and metabolomics, all the omics is another comics. It's necessary we have group, concentrate, focus in just particular area. Well, we can translate this thing of cascade from structural genomics to the transcriptomic, proteomics, etc. We can translate this idea in salmon culture. We can have that. It's more or less the same idea when we have a salmon genome sequencing. We are expecting to have the first draft of the genome in the end of the next year. Now in GenBank is when the first assembly with the threefold. In September, we are expecting to have another assembly of the 5 or 6-fold, and again, in the end of the next year, the first draft. When we have the first draft, for us, it's possible have a complete genetic map. With the complete genetic map, we can map or put flag in the molecular market between QTL, you know QTL, the region or genomic zone that responsibly ought to the response of some traits. For instance, resistant. Resistant is a very, very complicated trait. It's not just a typical Mendelian trait where just involve one gene. The immunological response involve a lot of genes. It may be 3 or 4 QTL, but each QTL is a very big sum of founded per base. When you have molecular marker, no molecular marker when they start and when they finish. So, if we have the genome, for instance, from this corner to the next corner, on this corner, all the genome, and we have flag of this marker, we can put this flag here when they start the QTL walk. We start the finish marker here, and we have the QTL. And we can map this QTL in this genome. And we can find what is the gene in this region? So, if there are a lot of genes, of course, but in this group of the gene, there are many genes with interest, with ontology to the response. So, for this is very important. Now, there are QTL to the growth, there are QTL to the color, there are QTL to resistance, there are QTL, blah, blah, blah. There are many QTL, a huge sum. All the people in this work, from the private company principal, are waiting to the genome, because these people take this QTL and put in the genome and say, oh, this is the gene, it's very interesting. Look, there are many genes in this QTL. Perfect. All the people is waiting that. So, of course, with the genetic map, we have the QTL, and we will overlap in the salmon genome, and we have, like say, one friend, rock and roll. And of course, of the, anyway, so we can go to the transcriptome when the most important technology in this area is macroarray, of course, and then we can go to the proteomics. When we have the annotation of the genome, we can pass without problem to the proteomics, and all this technology move to the look, what is the candidate gene? Candidate gene for everywhere. So, grow, resistant, color, blah, 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 blah. And we can apply this candidate gene in stock selection, product quality, pathogen interaction, therapy, etc., etc., etc. So, sometimes we have the trends of think that the life is very easy. It's very good. It's very good to wake up all days in the morning and think, okay, God, I can see the sun, the life is very beautiful, it's perfect. When we go to the laboratory, we to get face to face with the reality. And the reality say that maybe the life is not very easy. Why? The problem with the complex traits like immunoresponse is the hereditability. Hereditability is a quantitative concept, populational concept. I mean, it's a concept that involves what is the possibility, how it is the probability to I have one parental with any trait, for instance, grow, and how is the possibility or probability to trespass, to go this trait to the new generation. The heredity, like you know, is go to the 0 to 1. 1 is perfect heredity, is maybe like a clone, like a bacterial reproduction. All is the same. And the 0, I mean, I have a parent, I have some trait, but I have a very, very, very lower probability of transfer this trait to my child. That is the concept. The problem with the heredity is that maybe like trait like grow have a very high heredity, like 0.4 is very good. But the problem with the disease, with the monoresponse, the heredity to any pathology is very lower, 0.1, 0.2. So, what do you mean this in the reality? Very easy. I have one female resistant, I have one male resistant, I cross both parents, and I am waiting of the new generation is resistant. With the lower heredity, no. So we don't have guarantee of to cross two parents with the resistant and to get child with their system. That is the problem. So we need another alternative. Of course, here is very important in disease, in the response of disease of genomics, because we can get what is the gene involved in the response, particular gene. But the problem is that we have two interactions more, not just genetics or genomic, behavior and environmental. On each of these alternatives put own contribution. For instance, in immune response, the genetics maybe have a great interest and the behavior just a little interest, and the environmental control the environmental at a little interest. It's different, for instance, if we're looking, for instance, color. Color is just one important component of genetics, more in component of the behavior, and in component of the environmental principal diet. And so we need to make a balance between all these alternatives. We need to control environmental, we need to control of the behavior to apply genetics. Of course, in the closed system, like the salmon production or any animal production, we try to control it. And maybe sometimes it's more easy, sometimes it's more hard, but the idea is we can and we have the option to control the behavior and the environmental. So we need to maybe focus in genetics. This is a typical picture to demonstrate a principal chain of the transcriptome. Maybe if you have some child of 2 or 3 years old and you present both of these butterflies and the pupa, maybe this child say are different species. Maybe it's good. It's just one child of the 3 years. So we know that it's the same individual. It's the same individual. But did individual have different tissue, different protein, different expression? And the genome of this individual is different of this individual? No. It's the same genome, have the same gene. The only chain of the expression. This is the power of the gene expression. That's incredible. So we think that we think that the gene expression is very important in aquaculture, because maybe we can learn a lot of the profile of gene expression, principal in disease. So one postdoc 1 year ago of my laboratory made the question, okay, Rodrigo, where are we? Well, okay, we are here. So we have just one idea where we are. And the next question, of course, is where are we going? Sometimes it's complicated, but there are many directions. Some direction is closed, and another direction is open. But the idea is try to go in all the directions. And the principal advice is maybe go slowly, because maybe if we go very fast, maybe we have many problems. So this is a typical situation in all the still laboratory, in all the laboratory working in genome is typical. We have to fight with the typical idea of the gene expression on turn off. I can to turn off one gene, I can to turn on one gene, and nothing more. One linear thinking, you know, the typical paradigm of the molecular biology. One gene, one mRNA, transcription, translation, and protein. But this paradigm of molecular biology, now we know that don't work. It's not just one linear idea when turned off. Okay, I can turn on one gene and have one protein. Okay, I can turn off this gene and don't have this protein. No, it's not very easy. We know that we have, for instance, splicing. Splicing is the typical alternative to the many organisms to have a lesser amount of gene, but a huge amount of protein. It's typical in human, for instance. It's typical. In human, we have a very little amount of gene, but we have a lot of protein. That is one evolutive alternative or evolutive strategy the many organisms to have an economical genome, but a lot of protein. For instance, in some vegetal, some people think that there are not many splicing. For this reason, there are a lot of gene, yeah, very big genome in plants. But in salmon, we know now the splicing situation is very important. So when we get any gene, it's just the first step. Okay, I am very happy, I have this gene, perfect. But we know now, from this gene, I have different isoform, different alternative. So the next step, obligation of the next step is go to the isoform from this gene. So it's a very important work. It's not just to make a notation of the gene. It's make the notation and the splicing forms. So also we have another problem, microRNA. We know now it's typical from human, it's typical from the model organisms, where we know the interaction between mRNA and microRNA. MicroRNA put in the 3' of the mRNA and make regulation. All the time, maybe down regulation. So what did it mean in the practical? In the practical, say, okay, maybe I can have one gene with a lot of mRNA. Oh, I think this gene have a huge expression. Perfect, maybe. But how is the interaction of this gene with microRNA? Maybe a lot of microRNA can interact with this specific mRNA and make down-regulation. It's another alternative. So, complication after complication, complication after complication. Well, after of this complication and a lot of more complication, of course, we continue with our positive mentality, and we think in a very good model. For us, a very good model is a typical model from the typical experiment. The typical experiment, for instance, is make a challenge test, for instance, of the disease, when we have a lot of family, a lot of group, and put one specific virus, one specific pathogen, virus, bacteria, blah, blah, blah. And we make a challenge test, and we wait one time, a specific time for each pathology, for each pathogen, and we are lucky. We are lucky. We have animals with the low mortality in the time, and we have, of course, organisms with the high mortality. Some people think, okay, these individuals are resistant. here with a particular genotype, and another individual are not resistant, are family. So this group are susceptible. For that, are not interested for our model. Why? Because if we back to the first question 20 minutes ago, when I say, what is the problem? The vaccine, the immunostimulant, or the organisms? Remember? And I say, oh, I buy this vaccine, but this vaccine don't work. We may be another alternative, if you remember, is the guilty is not the vaccine, it's the organism. But we have now some platform, we have now some marker, molecular marker, to evaluate both hypotheses? No. But this model can give this option, but because these individuals, these organisms, make filter. So, if you have any organisms, for instance, a susceptible organisms, and you can transform these organisms with any vaccine, with any immunostimulant, in one resistant individuals, these susceptible organisms with this vaccine or with this immunostimulant need to show the same profile of the gene expression of this individual. But this individual are resistant and say, okay, guy, you can be like me, okay, so you have to turn on this gene because I know what is the gene that are necessary to make resistant. Why? Because I am resistant. So, is there any vaccine or any immunostimulant or antivirus, blah, blah, blah? No, antivirus no, but antivirus is, the target is the virus. Need to turn off the same gene. This is a very logic proposal. This is a very logic hypothesis. But for this hypothesis work, we need the resistant organism. This work with the resistant organism. If we don't have resistant organisms, we cannot work in this model. So our idea is not new. Maybe some modified idea, but Charles Darwin have the same area, some the same work in the same area, and have the same idea. So genetic variation exists between population. Individuals have different traits, of course, and differential reproduction. Those with best adaptation more likely to survive and reproduce. The fight of the more strong is typical thinking of Darwin. Here is the same. So our idea is not new. Our idea have a lot of years. Start with Darwin. Just we are looking to a similar idea, apply all the idea and hypotheses of the Darwin now in our era. So, but we have another complication. Maybe Darwin don't know that. What's the difference between resistance and tolerance? But it's very important. But the result of this issue is very different. Resistant is one individual with the capacity to stop of the replication of any virus or pathogen. It's important. I have the capacity to stop of the replication of any pathogen in my body. If you have this capacity, you have resistance. The resistant are most important because the resistant with this capacity are no vector to infect another individual. Why? Because it stops the replication of virus. This is a target. What is tolerance? It's another definition. It's one organism with the capacity to live in the time, but with the pathogen in the body, with the pathogen in own system. This is the tolerance. Tolerance is good also, but the problem with the tolerance is the tolerance can be vector to infect another individual. So the first idea is not just check with the challenge test if some family or some group live in the time. Oh, these individuals are resistant. No, this individual or this group or this family are candidate to be resistant. Not just resistant, it's candidate to be resistant. What we need to check first is this individual have the capacity to stop the replication of the virus. In this moment, these groups transform from the candidate to resistant to the resistant. So, with all this information, years ago, we start to work with IPM virus. IPM virus is very important virus of the fresh water in the salmoniculture and the many organisms, not just salmonid. Turbot, for instance, is another candidate of IPM. So we can see in this graphic a typical mortality curve when we have here, for instance, family with a few individuals. Oops, sorry. Mortality. Anyway, don't worry. And for instance, another family with a high level of the individuals with diet. So this family is not very interesting, but the first family in the first circle maybe is a candidate to make resistant. Very important. When we get this result, we are very happy. But we can say in my group, say, okay, perfect. We have candidate of resistance. So in this moment, we can start to work. But if we don't have resistance, we cannot work. So the first step is complete. Perfect. We have candidate to resistance. So this is another graphic with the same curve with a lot of family. These experiments are very, very expensive. It's very expensive. And are very contrary with the authority of my government. But we are making infection of the very, very dramatic, very, very dangerous virus. So we have all the inspector, all the people of the government shaking every step that you have in the everyday. It's very complicated. So we tried, for instance, in one time modulation, check typical profile of the gene expression of the in the time of the different gene. We don't have focus, sorry. Typical gene is interferons, TAP, MX1. Maybe we can see better in another slide. So the idea is the typical in the time post-infection, time 1, time 5 days, time 21 days, we have a typical trends of the several genes. We can have more expression from 1 day to the 1 day of infection to the day 5, and then done. That's it, for instance, STAT1. Another gene is in yellow, In yellow, you have, sorry, I can see well. Well, the idea is here we have the typical susceptible group for here. And here we have the trend of the resistant group. If you can compare it, both trends are very different. Here, don't work the expression of the gene. And here is work. For this reason, maybe these candidate genes are very important, or at least we think are involved in the immunoresponse. They are very classical genes, but it's very important. It's incredible, this comparison. All the people in many publications just make challenge tests, take a group, any group. For these people, don't matter what is the origin of this group, anywhere, wherever. Make the challenge test, make gene expression analysis, but what is the implication of the genetic background of each group is very important. We demonstrate that is very important, at least in the time modulation. So we make our, it's just one paper. We make a typical AST analysis. We construct library AST. It's a vertical experiment. Many laboratories that work in genomics. We make our web page. We are all the genes that we find in our library in both group, susceptible and resistant group. Well, but the first step is to know what is the gene involved in this response. We check here just for gene. We show here a lot of genes. So after, the next step, of course, was work with macroarray. And now there are different platforms of macroarray in salmonic, for truth, for Atlantic salmon, but I like very much the macroarray of my friend Ben Coop from the laboratory of the University of Victoria in Canada. It's a good group. We collaborate a lot with Ben. So we make a challenge test with macroarray experiment of IPN. The typical experiment with challenge, we have control. It's a typical experiment, you know very well that. With more time of modulation, with the typical analysis, and of course, with the comparison with qPCR. We work with the skin, spleen, and head kidney. But spleen and head kidneys are immunological tissue in fish. So, what happened? Well, we have, this is a summary. It's a little summary. We have no specific immunogene. We have a specific immunogene. We have transcription factor with a different profile of expression with the day. Of course, we have very important gene for us, apoptosis. It's very important. FAS, in the group of the specific gene CD8, a typical immunological gene. It's a surprise, important. MX protein, we expected this gene, but it's a favorite gene of the many immunological people. It's antivirus gene. Kupffer cell, there are many genes with there are many different. So what make now with all the list of genes? What is the problem with macroarray? Okay, we have a long list of genes. well, we have a group of genes, but we need to try to reduce this list of genes in one important gene. So this is the next publication. This publication is accepted in veterinary immunology and immunopathology with try to relationate the phenotype susceptibility or resistant with different gene expression, and we get very interesting results. So, for instance, we have here in the gene in the group of the immediately respond. So you know that we can separate the immunoresponse in adaptative and respond immediately, you know. So we can see here gene of the first group with the first response, and you can check, it's a typical graphic where you can see for individual, the line is the middle of the average, and the ACE is the susceptibility, R is the resistant, and the number is the day, 1 day, 5 day, 21 day. We can see that. Look on the first group, susceptible organisms, we can, the similar trends, we can start with expression, we can go to the plateau, and then we can down. And in another group, we start with the same trend, we start with expression, we can go to the maybe plateau, and we can continue with the up of the expression. It's very different. So all the publication just evaluate expression, maybe the same gene in any group, but don't make the comparison. And the comparison is very different. It's important if we are working with the resistant associated organisms to interpret to the gene expression result. It's very, very important. So maybe the only difference of the different pattern with the rest of gene is MX1, the very, very favorite gene of the many immunological people. Look, start, plateau, but not down. Stay in the same line with the more higher expression in the susceptible group. And here, the same. MX1 have the same trends of the expression between both groups. What is the conclusion of that? MX1 is not important. Wow! One referee say, please, you are trying to down the thing of the many years. Yes, we're trying to make that. Say to the immunological people, no, the MX1 is not important. At least in this response of this pathology. But if this gene were important, we can say different trends between resistant and between susceptible, but we don't have different trends. So this gene is not important. I mean, okay, of course, okay, it's important, right? But I am trying to explain the model of my model, right? It's not important for my model of the between resistant and susceptible. So this is very interesting. But many groups, many private companies, and many groups in Chile, Norway, and Canada use this gene to separate two organisms with response and organisms without response. So now, for these people, we have to say, okay, guys, we have to change the gene. This gene don't work more. So we have, of course, we have gene of the adaptive response, and the trends is very similar. We can start, we can go to the plateau, and we keep or down. So both response, typical response, present the same trend between resistant and susceptible organisms. So we make enrichment GO, gene ontology of our library and our microarray study. We can get of the immunoresponse of the cytokine activity is the most important category of the gene in the IPM response. So maybe we have to need concentrate in this area, in this the response of cytokine. So our idea, maybe we confirm our hypothesis with IPM at least, where we have different phenotype with different genotype with the influence in the state of the disease, but of course it's very important the environmental effect in our work model. So we make another publication in one specific paper in the journal, in aquaculture nutrition, but in some closed system like the salmon-linking, all the people try to control all the conditions. But maybe the more complicated condition now is give to all the fish one diet with vegetal protein. So we can try to evaluate what is the impact of this chain of the protein origin in the expression of the specific gene. We have to make this evaluation with the merge of the two experiments. One experiment with different diet and keep different diet more or less 2 months, and then to make a challenge test. But it's very logic that to express several immunological genes, you have to make first of activation of the gene. And the activation of the gene, what is a stimuli? The stimuli is pathogen. But again, make a challenge test is very complicated, it's very expensive, it's very expensive. And in this particular experiment, we make one experiment 2 months of the diet and to make a challenge test. Wow. So our idea was evaluate the gene expression of the lot of expression without challenge test. A very, very high risk. But we have a very interesting result with a specific gene, MX1. Because if you can look here, we have an expression of the gene in control. L is lupino. Sorry, I don't remember exactly what is the scientific name of the lupino. Lupino is one plant. We have here P, and we have here race. And what is more important here, you can see in this particular vegetal from 15%, the same origin with the 25 and the rice with 10, 20, 13. We have a different expression in comparison with the control. So if we give this diet from here to the feed, we have effect in the expression of the MX1. Well, for the referee of this journal, I think that is very important because it's one very good advice to the people to make diet with different vegetal. Say, okay, we cannot put in the diet 10% of the rice because this percent impact of the gene expression. Very practical idea. Well, we have to try to mix. I know this, I am jumping from different area because all the area, remember, is just transcriptomic, but all are related. We have one PhD of my laboratory say, okay, Rodrigo, now it's time to evaluate the microRNA. Perfect. We try to go towards the microRNA in salmon. There are no microRNA. Nothing said, they're nothing. So we can start from zero. So we are talking with my bioinformatics group in my lab and say, okay, guys, we have a new task, and to try to find microRNA in salmon. So we have a typical bioinformatics journal, very important, bioinformation. This is a look of our web page. We look where is the microRNA in salmon, but with particular focus in immunological gene. So our first task was to get all the immunological gene to know in salmon and try to evaluate in silico way the presence of the microRNA, the target of the microRNA. So this is a very intuitive slide. You can see here the name of the microRNA, all the dates, and the most important here, you can see the target. So it's very important because people from Norway in this moment open a lot of our web page because they can, or anyway, can check any gene and check if this gene have a target to microRNA. Okay? So this investigator or these people can think in this moment, okay, careful with this gene, but this gene maybe can be controlled, not just for the typical expression, also with the one microRNA. So this is very, very, very important. This is a web page. We can check a lot of alternatives. This is the same with a lot. This is the idea is show you a lot of microRNA. They are new and old microRNA. And the next step is to link the transcriptomic or the gene expression with the structural genomics. So currently, there are a big discussion. We talked 20 minutes ago about heritability of trait, but what is the heritability of the gene expression? I mean, okay, I have one expression in one particular gene or in one particular group. My son have the same expression that me? Look, careful. I don't talking about the physical trait, color, growth. No. I am talking about expression. My child have the same expression that me? It's complicated. The gene expression have heritability? It's a very complicated issue. Yet in this area, it's very, very important, epigenomics. In this area is key, the work of epigenomics. So the most classical way to work in this problem is try to change to the transcriptomic to structural genomics. And the more characteristical example of the genomic, structural genomic is SNP, single nucleotide polymorphism. You know that is very quickly. You know that the polymorphism is very important because we can look one polymorphism or SNP in one very particular position in very particular region of the gene, maybe we can relationate the effect of the dominant regulation of the gene with the presence of the SNP. It's very typical. So we are working to relationate LD or linkage disequilibrium. You know that we have recombination between both parents with diploid organisms. So the idea is try to evaluate one very little position of a SNP, but the SNP is, for definition, conserved. So we don't have lose the SNP with recombination. So we are looking a lot of SNP with LD. So this SNP is with LD or linkage disequilibrium with another SNP, with another SNP, with another SNP. So we have a haplotype, we have a tag to try to not lose this SNP with the recombination. So we have in this journal published recently a lot of SNP, in silico SNP, again with the focus in immunological organs, kidney, liver, spleen. With here's the frequency of SNP from different genes, of course, in each organ. And we have here in gene ontology category, biological process, molecular function, of all our genes. Maybe if we can see with the detail, here we can see of the immune system is here, for instance, here, as is not very higher. So all the idea is say, okay, maybe it's now to think that the typical immunological gene athlete in fish are not, of course, are important, but are not very, very, very important. Maybe another gene is participating, of course, in the response with more relevant than the immunological gene. It's very important. So now we have a lot of SNP to evaluate in all the genes, a lot of immunological gene. So we have moved very fast, but you know that now we have is very quickly of the change of the technology, and we have not just the Sanger sequencing, this is old-fashioned, but we have the second wave of the technology of sequencing. I am talking about sequencing by Illumina, Roche, with the 454, solid from Apply, and it's come very quickly another wave of generation of sequencing with the Ion Torrent ATC, where we have is very excellent field of sequence. It's very, 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 very interesting. So we have here more or less typical. This is typical slide from Stratton. We are here. In this moment. We start with the high-proof sequencing, with the pyro sequencing, with the next generation. So all the people is moving from sequencing with Sanger to the next generation. All the people is moving from microarray to RNA transcriptomic with the second wave of the technology of generation. It's very important. We have some example of machine of the second wave. We have the Illumina HiSec with different machine. We have, for instance, make library per mate or library single library, very, very simple. But the most important is this column. You can see, for instance, the amount of the data. For instance, you can make a per mate library of the 15 per base, per read. Per mate is to read. We have millions of read. Million. The problem with this technology is the length of the read. It's very short. But if we want more longer read, we can move to the 454. But the problem with we got more longer read. But the problem with 454 is we get a lesser amount of data. So if we make transcriptomic, the perfect candidate is Illumina. It's very typical. I can talk more of the solid because solid is the worst technology. The most popular is Illumina and 454. That you can put in any search, for instance, PubMed Illumina, and you can get a lot of results. So we can make another challenge test, but it's in this case with ISA. It's a very problematic problem to make country. We started with the ISA 4 years ago. Many people lose the job. It's a very critical social situation, very critical. But our hypothesis here is try to relationate the genome background with the vaccine. Well, very interesting. What is the idea? We cross our finger to try to find the similar situation with the IPN, I mean resistant family. But we put now in this model another complication, vaccine. So you can see in the red line the typical control with the high mortality. You can see here, for instance, the SNEER. SNEER is the group resistant. FANAT is the group susceptible. CB is, here is in Spanish, is with vaccine. Is without vaccine, okay? So, you can see here in the resistant group with vaccine, this line, and compare the same group but without vaccine, the green line, you can compare that, apply this particular vaccine. It's a commercial vaccine. It's a commercial vaccine. You can see what is the effect of the vaccine in this resistant line. You can move from this mortality to this another mortality. This mortality is low, but it's resistant. But if you put vaccine in this group, you get this mortality, more or less 13% of the difference. Wow, that's incredible. And if you can see the susceptible organisms, for instance, this group, yellow, without vaccine, and the blue with vaccine. Of course, the yellow is the more susceptible organisms, family, so have the more higher mortality. We are awaiting that. Perfect. The yellow line. And if you vaccine this group, you can move here. The vaccine is working. But the vaccine works better in the resistant group. So for any people working in any farm, it's more economical have resistant group. But with any vaccine, in particular with this vaccine, he can to reduce the mortality of this group. So the vaccine is more effective in one resistant group. It's effective in one susceptible group, right? But it's more effective in one resistant group. This is a good demonstration of the interaction genome background and vaccine. So we make an Illumina sequencing of the different strain. We have 6 library per mate library. We have technical replicate, having the same idea as some microarray. We have biological replicate. And we have, of course, library, the organisms from the spleen, the organ. With vaccine, without vaccine, strain 1 is the susceptible, strain 2 is the resistant, and we have in the strain 2 with vaccine, the replicate, and of course, without vaccine. So we can, you can see there in this column the number of the raw data, 100 per base, each read with Illumina. We are talking about 310 million of read, 310 million of read. Bioinformatics, we need a huge capacity of storage to keep this information. Well, that's incredible. So in this moment, many people can use this technology, but the problem is not make the library, but the problem is not make the sequencing. Of course, there are practical problems, but it's not very important. What is the more important problem? The bioinformatic analysis. If you don't have a very, very strong bioinformatic group, the ideas maybe don't work with this technology, but it's very complicated. We are talking about the million of read. So this is the typical pipeline of the, have a lot of steps of the Illumina, where the trimming, the trimming is purified each read with repetition, with duplicate, etc. We have the assembly with, in red is the software with Trinity of the each library. So we have 6 assembled. And then we merge all the 6 assembled, and we have the first transcripts of reference in Salar. And with reference transcriptome, we make functional annotation. We make mapping of the raw read in this reference. It's a typical pipeline, it's characteristic. And we have the calculate different expression with the list of the different expression gene, and with the finish make a gene enrichment of the gene ontology. So we have the same number. In this column is the raw data, million of read. We pass of this column to this another column. This is the clean data of the trimming, etc. So we have a big reduction of the number of read, a big reduction. So after we have the first assemble of each library. The typical N15 is very good. The more short is 100 per base. The contig is very good, and the more larger is 20,000, more or less. Now, here is the lesser length, but the numbers are good. These are typical number of the bioinformatic guide. So we have here the first transcriptome reference from the 6th library. We have the number of contig, 158 contig. With the M15 is very good. With the smaller is not very good. Is the more smaller contig is the 68 per base is very smaller, but the more longer is very important. Is more longer. So it's a very good news. So the problem is this amount of contig, the first here, we have just this amount of annotated gene. Nothing. And the more higher amount of data is unknown. Why? We don't have database in GenBank, for instance, or any database to make comparative genomics to annotate the gene. Don't have. So for this reason, also it's very important to wait the annotation of the genome. But in this moment, we have just a few number of gene with annotation. The number of genes with more information is more dramatic. 6% of gene with AC number, so we can relationate the name of gene with some specific enzyme. 12% of gene with geo terms. 8% with gene with domains. Very complicated. So anyway, we continue with the project, and we make a typical statistical analysis like an ANOVA of just one level. It's a typical condition. Condition, for instance, this is just one example. Condition resistant, condition susceptible, with vaccine, without vaccine, the typical statistical analysis. And we can see here, first, the gene ontology of this person of gene, or 1%. This is the principal category. Maybe the most important category is biological process. We can see the most important is cellular process. Now, again, immunological process. We can see, I lose some information. Yes. Sorry. So the idea here is compare the information of this gene, and in this group, with the comparison of the differentiation between phenotypes and with vaccine, phenotype susceptible and phenotype resistant. With vaccine, the differences, I lose the slide, but it's not very important because it's a very similar table. It's just 15 genes. So 15 genes are responsible to the difference between resistant and susceptible with vaccine. 15 genes, nothing more. That's very important because we have a few number of genes that explain this difference. Of this group, the resistant and susceptible group are just have explanation of the 15 gene, nothing more. So many people think that we present this result, say, okay, Rodrigo, but you can say that this all the gene? No, of course. It's just the start. But we have to start from 1 point, and 1 point is on 15 genes. Of course, there are more genes involved in the response, but we are maybe now the most important gene. So the idea now in this moment is apply this gene, qPCR, SNP, and microRNA, and of course, epigenomics. But we are starting from 1 point. That is very important. Well, we have a problem with my last This is my collaborator now in different parts of this world. There are many people, so sometimes I put a list, the name, but it's very long. If some people say, okay, no, Rodrigo, don't put more this list. So I put the group, nothing more. It's a very good group. So thank you for that. Thank you for your attention. Gracias. Y si anyway have question in Spanish or English,